Hello everyone and welcome back for the beginning of the second semester of pre-calc. I hope all your exams have gone well and you're looking forward to this semester and we're halfway done and summer is quickly approaching now. So today we're going to start with chapter 5. Chapter 5 really looks at a couple different things. Number one, it looks at the unit circle and then looks at graphing the various trig functions. So we will spend time today in this video working with the unit circle, but then in the next couple videos, we'll be looking at graphing of the trig functions and sine, cosine, and then the other four. Also, remember, if you take a look at the schedule, you'll notice that we are going to be spending 2 days on Chapter 5, Section 2. So there actually should be, I think there will be, my plan right now is to do 2 videos. The one video will deal with the graphing of the sine, cosine functions, looking at the various characteristics that you need to identify. And then the other one will be dealing with some of the combining of these functions and how to graph those out. So that's where we'll go there. And then the last one will be with graphing the other 4. So to start out with today, we are looking at the unit circle. We're going to look at the unit circle approach. Our skill objectives for this video are number 1, to draw the unit circle showing the special angles and label cosine and sine values. Number 2, determine the domain and range of the trigonometric or otherwise known as circular functions. And 3, classify the trig functions as either even or odd. The 6 trig functions will be some of them are even, some of them are odd, none of them are neither. So you don't have to worry about that aspect. Our conceptual objectives for this video. Number 1, understand the unit circle approach is consistent with previous definitions of trig functions. Number 2, relate the points on the unit circle to the values of cosine and sine functions. And 3, visualize the periodic properties of the trigonometric functions. Let's start out looking at the unit circle. Now, the unit circle is a circle with radius 1. Okay, now because of that, remember, one time around the circle in terms of theta, if I just rotate my angle theta right here, one time around that circle is equal to 2 pi radians. And what's important to remember, because of the circumference, when you have a unit circle, the radian measure of the angle is equal to the arc length of that intercepted arc. So if I say this angle is theta, I know this arc has a measure of theta as well. Now my angle that's theta is going to be rotated through, and it's going to go through the point xy, and I can drop that perpendicular. Now what that does for me is it really ties this into the SOHCAHTOA definition, as well as the other one where we dealt with the point going through the terminal side and looking at it in terms of the sine and cosine as either being the x or the y coordinate over the radius, the r value, the distance from the terminal, the endpoint to the origin. So what happens on this, because of that definition, or SOHCAHTOA, however you want to look at it, I know that this length right there, that is equal to y, and I know this length here is equal to x. And so if I want to label that, this is going to be x, and this length right over here, well, it's going to be a little bit harder, is y. That's that length right there. Now, because of that, I know by SOHCAHTOA that the sine of this angle right there is opposite over hypotenuse, so I'll get sine of theta equals y over 1, which is y. And the cosine of theta is adjacent over hypotenuse, so cosine of theta is equal to x over 1, which is x. And so it's real important for you to recognize that the cosine of an angle, the value of that cosine function is going to be the x-coordinate of a point on the unit circle, and the sine of an angle is going to be the y-coordinate of a point on the unit circle. So we're going to come down here, we'll let x and y, xy, be any point on the unit circle. If theta is a real number that represents the distance from the point 1, 0 along the circumference of to the point xy, then the cosine of theta equals x, the sine of theta equals y, which is what we just found out, tangent, which is should be very familiar. You should remember this one. Tangent of theta is y over x because we've dealt with that. That was from our one of our previous definitions that we had as well. And x does not equal 0 here because we can't have a 0 on the bottom. The secant of theta we know is the reciprocal of cosine, so that's going to be 1 over x, where x does not equal 0. The cosecant of theta is going to be 1 over y, which is because, and that should make sense again because cosecant is the reciprocal of sine, so that's y does not equal 0. And the cotangent, which is the reciprocal of tangent, is going to be the x value over the y value, again, where y does not equal 0. Now, because of the reciprocal relationships, it's really key that you recognize these top three for sure, and then use the reciprocal relationships to derive the other three. But if you remember cosine is x, sine is y, and tangent is y over x, you can get the secant, cosecant, cotangent. Another thing that I used that helped me go through with remembering on things, remembering which one cosine was and sine. Again, I just use the alphabetical order. X comes before y alphabetically. Cosine would come before sine alphabetically. Cosine goes with x, sine goes with y. Whatever will help you remember that is going to be key, and you need to make sure that you do get that down. So let's take a look at a couple examples. In this case, this first example, we're going to look at the sine of 5 pi over 6. Well, what I'm going to do is I'm going to go to 5 pi over 6, which happens to be right here. And I know that the sine of 5 pi over 6 is going to be the y-coordinate of the point associated with the 5 pi over 6 here. And that point is negative square root 3 over 2 and 1/2. So therefore, I know that the sine of 5 pi over 6 is going to be equal to 1/2. The cosine of 7 pi over 4. Cosine of 7 pi over 4. Locate the 7 pi over 4. 7 pi over 4 is right over here. That's on the unit circle. And you can identify the point there as the square root 2 over 2, negative square root 2 over 2. Cosine is the x-coordinate. So in this case, the cosine of 7 pi over 4 is going to equal positive square root 2 over 2. Now let's take a look at a couple others. The first one I want to look at is the tangent of 2 pi over 3. Now 2 pi over 3 is right here, so I have to find that point. Now I remember tangent is y over x. So in this case, the point associated 2 pi over 3 is negative 1/2 square root 3 over 2. So I know in this case the tangent of 2 pi over 3 is going to equal y over x square root 3 over 2 all over 1/2, which that's a negative 1/2. Well, now that, when I divide by negative 1/2, that I know is going to be square root 3 over 2 times negative 2 over 1. And when I simplify it, the 2's will drop off, and I get that the tangent of 2 pi over 3 comes out to be negative square root of 3. So that's negative square root 3. Now, with the tangent of 3 pi over 2, tangent of 3 pi over 2, when I go to 3 pi over 2, which is right down here, the point associated with that is the point 0, negative 1. Now, tangent at that point, tangent again is y over x. So in this case, when I look at the tangent here of 3 pi over 2, I'm going to do this one in white, I'm going to get the y-coordinate negative 1 over 0. Well, we know that division by 0 is not allowed, so therefore, in this situation here, the tangent of 3 pi over 2 is said to be undefined. Now, graphically, when we look at a tangent function there, you're going to notice when I deal with when I deal with a number other than 0 over 0, I can think of that really as getting to be a very, very large. It's going to go off to positive or negative infinity. So what we have in this situation, when we see this behavior, this type of situation right there, -1/0, that's telling me we have a vertical asymptote, and so the function values are going to get as we move closer to that, closer to 3 pi over 2, my tangent values are going to go way off towards negative infinity in this case. Another thing they're going to ask you to do from the unit circle is going to be to solve a particular equation, identify angles that make an equation true. So in this case, what we're going to be looking at a lot of times, in this case, we're looking at the values of theta going from 0 to 2 pi. And so what we want to do is we want to identify every solution between 0 and 2 pi for what that will make my equation true. For example, let's look at the first one. Sine of theta equals square root 3 over 2. So what I need to do is I need to identify every angle, every location that has a y-coordinate of square root 3 over 2. So in this case, when I look at those y-coordinates, and we're looking at the ones in blue, I see a square root 3 over 2 right here, and I see another one right here. Now this particular one is associated with pi over 3. So one of my solutions in this case is going to be that theta is equal to pi over 3. Or the other one that I look at when I notice it's over here, that happens to be at 2 pi over 3. So I would say that pi over 3 and 2 pi over 3. What I'd like you to do right now is pause the video, and I'd like you to identify the angles that would make this second equation true, that the cosine of theta is equal to -1/2. Pause the video and identify those values of theta. Welcome back. In this case, with the cosine equal to -1/2, you should have located that there were two values. Again, we're looking, cosine is the x value, where we have that, and one location that's -1/2 is here, and another one is right down here. This one is associated with 2 pi over 3, and -1/2 down here is associated with 4 pi over 3. So what you should have gotten in this case would be that theta would be equal to 2 pi over 3 or 4 pi over 3. Again, we are looking only from 0 to 2 pi, so I don't have to look at anything that would be coterminal to those as well. The next ones I want to look at are really looking at the what are called quadrantal angles. They're the ones that are on the quadrants, not or on the borders of the quadrant, on the axes. What we have is the sine of theta equal to 0. Again, sine of theta is the y-coordinate. So that means the y-coordinate is 0, and we notice that that's 0 at these two locations. Now, because of how we have this written out, the sine of theta equal to 0, we actually have to have, it's one of the few times, it's about the only time that you're going to see where we have three solutions on this, because we are going through, the way this is set up, we're finding all the values from 0 less than or equal to theta less than or equal to 2 pi. Now, sometimes I've seen it where that's just a less than. But right now what I have on this one is less than or equal to. So in this case, the values for theta, well, this first one here, that one is at when theta is equal to 0. So we would get 0. It also happens at pi, and then again at 2 pi. The cosine of theta is equal to 0. Cosine of theta, that's the x-coordinate 0, is here. And here there are just two solutions on this one, and that happens to be at pi over 2 and 3 pi over 2. Now I want to recognize that for a couple different reasons. Number one, you're going to notice here with this first one, with the sine of theta equal to 0. Yes, it's at 0 pi, 2 pi, but you probably can recognize a pattern pretty quick and say, oh, it's going to be also 0 at 3 pi, 4 pi, 5 pi, so forth, as well as going in the negatives. -1 pi, -2 pi, -3 pi are all going to have a sign value of 0. Here, with this one right here, where the cosine is 0, that's at pi over 2, 3 pi over 2. But you might recognize saying, oh, wait, there appears to be something here. We could say 5 pi over 2 would be another one, 7 pi over 2, 9 pi over 2, and again going in the negative direction as well. So what you notice on this, in terms of these, is that sine is 0 whenever we have an integer multiple of pi. Sine is going to be 0 whenever you have something in the form of some integer n times pi. Cosine is going to be 0 when we have an odd multiple of pi in the numerator and a 2 in the denominator. Well, odd multiples are going to be, that's going to be when we have 2n plus 1, that is always going to be an odd number, times pi over 2. So when we have an integer multiple of pi, I know the sign is going to be 0. When I have an odd multiple of pi divided by 2, I know that the cosine is going to be 0. Now, why is that important? Well, that's important because of the fact that we have trig functions that involve a division by sine or cosine. I know that the secant is 1 divided by cosine. So every place that the cosine is equal to 0, that's going to make the secant undefined. Same with tangent. Tangent is sine divided by cosine. So every time the cosine is equal to 0, my tangent function is going to be undefined. And I'm going to have vertical asymptotes for those functions at those locations. With the sine, when cosecant is a reciprocal of sine, so I have vertical asymptotes when the sine is equal to 0. And same with cotangent. Cotangent is cosine divided by sine. And so when sine is equal to 0, I know the cotangent is going to be undefined and therefore have a vertical asymptote as well. This now leads us to the domains and ranges of these trig functions. Let's start out with sine and cosine, these two right here. Okay, they are very similar. With the sine value, the domain on this is for sine and cosine, there's both all real numbers, negative infinity to infinity. And the range is going from -1 to 1, including those. Remember, the highest value you can get for sine and cosine is 1. The lowest value you can get for sine or cosine is -1. We can't go outside of that range. Tangent. With the tangent, we know that the domain on this is going to be all reals except where the cosine is equal to 0. So that means except when all reals, except when theta, such that theta does not equal that 2n plus 1 times pi over 2, the odd multiples of pi. Now also because the tangent does have vertical asymptotes here, and because of the relationship it does have, it can be 0. It can be negative, it can be positive. It is going to go, its range is all real numbers from negative infinity to infinity. Cotangent. Cotangent right here, domain, again, cotangent is cosine divided by sine. So every place the sine is equal to 0 needs to be eliminated. So in this case, the cotangent, the domain of the cotangent, is all real such that theta does not equal n times pi, an integer multiple of pi. And again, like tangent, the range on the cotangent function is negative infinity to infinity. Secant. Secant is all reals except where cosine is 0, so it's going to have the same domain as the tangent. It's all reals such that st is such that theta does not equal the 2n plus 1 times pi over 2, the odd multiples of pi in the numerator divided by 2. Now, secant and cosecant are unique in that since they are reciprocals of sine and cosine, when I take the reciprocal of a number between -1 and 1, I'm going to get something that is outside of that. For example, 1/2 falls as a possible cosine value. If the cosine of the angle is 1/2, that would mean that the secant would be 2. So we're outside. We're bigger than 1. And if I said that the cosine value was, let's say, -1/7, then the secant would be the reciprocal of that, which would be -7. And so for that reason, we do have vertical asymptotes, so our range is going to go off towards negative infinity to positive infinity. But in this case, it is actually joining two pieces. It's the negative infinity to -1, including -1, union with 1 to infinity. Cosecant of theta, very similar to the secant in that it's all reals, but this time such that theta does not equal n pi, because it cannot be an integer multiple of pi, because it will be the cosecant will be undefined there. And its range is also going to be from negative infinity to -1, union 1 to infinity. And please note, in these two here, the secant and cosecant, we do include the 1 and -1 in our range. At this point, please make sure this is written down in your notes. You are ready for this. You will need to become very familiar with the domain and ranges of these 6 trig functions, because that is going to come up numerous times as we progress through this class. Now let's get to the even and odd. One thing I want to do is I want you to recall that if f of x, if a function is even, that means that f of the opposite of x will equal f of x. And graphically what that meant was that functions that were even were symmetric about or over the y-axis. So even functions are symmetric over the y-axis. And I always say, what I kind of say about it is that when I put opposites into the function, I will get the same result out. For example, x squared. X squared is an even function. When I put 2 in to x squared, I get 4. When I put -2 in, -2 squared is going to be also going to be a positive 4. If f of x is odd, if f of x is an odd function, then that means that when I put a negative f, the opposite of x into function f, I'm going to get the opposite of f of x. Okay. And remember on this one, these are symmetric about the origin. Now, our 6 trig functions are going to be classified as either even or odd. So let's take a look at those. Now, you'll notice here I have a unit circle right over here. And one of the things you have to remember is that the angles that are labeled are showing one counterclockwise rotation around the circle. But we know that we can go multiple rotations, counterclockwise or clockwise. When I rotate clockwise, I remember that those are negative angle measures. So when I talk about the cosine of pi over 3, I can go to pi over 3, which is here, and I look at the point associated with it, and I know that the cosine of pi over 3 is a positive 1/2. Now when I look at the cosine of negative pi over 3, right there, negative pi over 3 means I am rotating in the clockwise direction pi over 3 units. Well, pi over 3 units counterclockwise is this part. When I go clockwise, it's going to here. So I know that this angle right there, when I go clockwise, that is going to be not 5 pi over 3, but I'll count that as negative pi over 3. And I know the cosine is the x-coordinate, so the cosine of negative pi over 3 is equal to 1/2. What I'd like you to do right now is I'd like you to pause the video, and I would like you to go and do the next two, cosine and the cosine of 2 pi over 3 and cosine of negative 2 pi over 3. Once you've done with that, go ahead and do the ones with sine as well. Sine of pi over 4, sine of negative pi over 4, sine of 5 pi over 6, and then the sine of negative 5 pi over 6. So pause the video and do those very similar to what I did in terms of calculating that one. Okay, welcome back. When you did this one, you should have come up that the cosine of 2 pi over 3 was negative 1/2. 2 pi over 3 is here. The cosine is the y-coordinate, or the x-coordinate, sorry. The x-coordinate in red is negative 1/2. And negative 2 pi over 3. Negative 2 pi over 3 is going to go and travel in like this all the way over here to what is labeled as 4 pi over 3. That would be negative 2 pi over 3, and it is negative 1/2 as well. Looking at the sign of pi over 4. Pi over 4 is here. The sign is the y-coordinate, and I get that is square root 2 over 2. When I go to negative pi over 4, it's going to go clockwise pi over 4 units, which gets me to this point right there, which is labeled 7 pi over 4. And the sign value there, you should have come up with negative square root 2 over 2. When I look at 5 pi over 6, 5 pi over 6 is over here. The sign value is 1/2. And I go negative 5 pi over 6. That's going to come all the way over to this point, and it is equal to a negative 1/2. Now you should notice some patterns here. Looking at cosine, when I see that these opposites gave me the same value, these opposite angles, 2 pi over 3 and negative 2 pi over 3, gave me the same value. I have the idea when I look at this, this would be an even function, that the cosine of negative theta would be equal to the cosine of theta. And when I look at these right here, opposites here, pi over 4, negative pi over 4, I got opposite results here as well. So this would lead me, you should be sitting there thinking that cosine is an even function and sine would be an odd function. So what we end up with here is up here cosine of negative theta will be equal to the cosine of theta, and we can see that from what we had in what we saw in the previous slide. And the sine of negative theta is going to be negative sine of theta. We know that. Now, because secant is the reciprocal of cosine, it shouldn't be any surprise that secant is also an even function. And so I would have that the secant of negative theta is also equal to the secant of theta as well. And the same can be true with cosecant. We know cosecant is the reciprocal of sine, and so what happens there is that since sine is an odd function, I know that cosecant is also an odd function. So cosecant of negative theta is going to be negative cosecant of theta. And the same thing is true with tangent and cotangent. I will do a proof to show you that tangent and cotangent are actually odd functions. But for right now, for what our notes right now, just realize that they happen to be odd functions. I'll show you the proof in class next time. It is going to be negative, tangent of negative theta will be negative tangent of theta. And cotangent of negative theta is going to be negative cotangent of theta. So now let's see an example of a problem, how this would work. We're going to find the tangent of negative 4 pi over 3. Well, I know the tangent of negative 4 pi over 3 is going to be equal to, because tangent is that's going to be the negative, by the identity we just saw, negative tangent of positive 4 pi over 3. And I know the tangent of 4 pi over 3 is going to be the y-coordinate over the x-coordinate. So I go to 4 pi over 3, which is here. And I know that the y-coordinate is negative square root 3 over 2. The x-coordinate is negative 1/2. And so I know that this is going to be equal to negative, the negative out in front there. And then it's going to be the y-coordinate, which is negative square root 3 over 2, all over a negative 1/2. Now we just have to simplify it. Well, the first thing I want you to do is notice you do have here those two negative signs. And so those two will cancel each other out. So that'll make that a positive and positive. So that's going to be the opposite negative of the square root 3 over 2 over positive 1/2. And now that because we're dividing by 1/2, that is going to be negative square root 3 over 2 times 2 over 1. The 2's drop off, and so I'm going to get a negative square root 3. So the tangent of negative 4 pi over 3 is going to be a negative square root 3. Now this does conclude the video that we have on this one. Couple things you should, if you remember if you still have your unit circle that you made last year, I'm assuming you did the last few years. They've told me they made them, and some people even still had them. If you have it, you're going to want to find it because you can refer to it. If you don't, that's no problem. I will put a unit circle onto Edmodo that you can download. But please remember, you do need to get this memorized. The unit circle, you may refer to it right now, but very soon you are going to need to have it memorized, and for the test and for actually some of the other chapters coming up as well. So work on getting that one memorized. Some of you might remember how how Mr. Gilbert, I've had a lot of people tell me that the way Mr. Gilbert explained it, they were very comfortable with it. That's fine. If you know that method for labeling and identifying, remembering the unit circle, great, use it. If not, talk to me. There are a number of different patterns that you can use to help you remember that unit circle, at least the points. And one key that you need to remember here is that you know how transformations work. And if you can remember the first quadrant, you can really use the transformations to help you label all the others. So with that, we'll talk some more about that in class. But as of right now, again, looking forward to the start of the second semester, and hopefully this semester will go fast and will be a good one for all of us. So have a good evening, and we'll see you at our next class.